Drop below 200 meters and the world changes. Sunlight, which floods the surface ocean, fades to a dim blue haze. By 1,000 meters, it is gone entirely. This is the midnight zone, a layer of the ocean that begins here and extends downward for thousands of meters, holding the largest habitat on Earth. No dawn reaches it. No shadow crosses it. It is a realm of permanent, absolute night. And to a human mind, darkness feels like safety. Close your eyes in a black room, and you vanish. It seems obvious that in a place without light, everything should be invisible. A fish hanging motionless in this void should be impossible to find. Nothing to reflect, nothing to betray a silhouette, nothing to give away the shape of a body against the black. For centuries, this was the assumption. The deep was imagined as a blind, empty vault where creatures drifted unseen through endless night, protected by the simple absence of the sun. But that assumption is wrong. Darkness, it turns out, guarantees nothing. The deep sea is not truly dark. It flickers, it sparks, it glows. Somewhere between 80 and 90% of the animals living here can produce their own light, a chemical fire generated inside their bodies. A single flash can rip the darkness open. And in that instant, anything nearby becomes visible, its outline thrown into sudden relief, its position exposed to whatever is watching. So the creatures of the deep face a paradox. They live surrounded by blackness, yet they cannot rely on it to hide. The very cover that should protect them can turn traitor at any moment, betrayed by the light their neighbors carry. To survive, an animal here must do more than simply exist in the dark. It must become part of the dark, so complete in its absorption of light that even a direct flash reveals nothing at all. This is a problem far harder than it sounds, a problem that ordinary black skin cannot solve. To understand why, we first have to understand the weapon that makes the deep so treacherous: the light itself. The light of the deep sea has a name: bioluminescence. It is produced when a molecule called luciferin reacts with oxygen, catalyzed by an enzyme, releasing energy not as heat, but as cold light. Blue-green is the dominant color, tuned to travel farthest through seawater. And down here, it is everywhere. Lanternfish carry rows of glowing organs along their flanks. Dragonfish sport light-producing patches beneath their eyes. Comb jellies scatter shimmering trails, and dinoflagellates flare when disturbed, painting the water with sudden sparks. In this environment, light is not decoration. It is a tool, a signal, and a weapon. Consider a predator gliding through the black, hunting by ambush. It closes on a target it cannot yet see. Then a nearby organism flashes, or the predator's own body catches a stray glow. In that fraction of a second, light strikes the predator's skin. If any of that light bounces back, its shape appears against the dark, and the prey it was stalking bolts, warned in time to escape. The ambush collapses. Now flip the situation. A small fish drifts in the open, trying to remain unseen. A hunting animal sweeps the water with its own searchlight, a built-in beam scanning for silhouettes. If the small fish's body reflects even a whisper of that beam, it lights up like a coin at the bottom of a well. Detected, it is dead. This is the treachery of light in the deep. Every flash is a double-edged blade. It can reveal prey to a hunter, or reveal a hunter to prey, or expose either one to a third party waiting in the dark. In an environment this sensitive, the smallest reflection carries enormous consequences. A surface that returns just a few % of incoming light is not camouflaged. It is a beacon. Survival, therefore, comes down to a brutal optical challenge. An animal must reflect almost nothing, no matter what light hits it, from any angle, at any moment. It must swallow the flash whole. In 2020, a team of scientists revealed just how far evolution had gone to meet that demand, uncovering a group of fish that had crossed a threshold no one expected. In July 2020, a study published in the journal Current Biology delivered a startling answer to the deep sea's optical problem. The research was led by Karen Osborne, a zoologist at the Smithsonian National Museum of Natural History, working with Alexander Davis, a biologist then at Duke University. Their subject was a group of fish so dark they had nearly defeated the very instruments meant to study them. The story began with frustration. Osborne's team had been photographing deep-sea animals hauled up from the water off Monterey Bay, California, and the Gulf of Mexico. Certain fish refused to photograph properly. No matter how the lights were arranged, no matter how powerful the flash, the cameras captured only a featureless black smear where a body should be. The fish were absorbing so much light that their shape, their fins, their texture simply would not register. That failure became the discovery. The researchers measured how much light the skin actually reflected, and the numbers were extraordinary. Across the specimens they examined, they identified at least 16 species whose skin reflected less than 0.5% of the light striking it. In other words, more than 99.5% of incoming light was captured and never returned. These were not close relatives. They spanned wildly different branches of the fish family tree, from the fanged dragonfish to the Pacific black dragon to the crown jewel of the set, a species called omerodes, an anglerfish whose skin measured among the darkest ever recorded in a living animal, reflecting as little as 0.044%. To grasp that benchmark, picture a threshold. Engineers generally call a material ultra-black once it reflects less than 0.5% of light. By that definition, these fish qualified outright. Evolution, with no laboratory and no design plan, had produced surfaces rivaling the blackest materials human beings can manufacture, and it had done so simply to survive in the dark. But this raises an obvious question. Black pigment already exists throughout the animal kingdom. Fish, birds, and mammals are full of it. So why isn't ordinary black skin enough? Why did these species need to reach so far beyond it? The answer lies in how normal black actually behaves. Think about the blackest everyday objects you know. A fresh coat of matte black paint. A charcoal briquette. A raven's feather. To our eyes, they look completely dark. But measured with instruments, ordinary black surfaces typically reflect somewhere between 2 and 10% of the light that hits them. Even high-quality black paint rarely drops below a few percent. That small leftover reflection is why you can still see the shape of a black car at night or the folds in a black shirt. The surface is dark, but it is not a void. It still hands light back to your eye. In the sunlit world, a few percent hardly matters, but in the deep sea, it is fatal. Remember the math of survival there. A flash of bioluminescence can strike from any direction, and any reflected light betrays a silhouette. A fish reflecting even 2% would glow faintly against the black, enough for a hunting predator's eye, tuned by evolution to detect the slightest contrast, to lock on. Ordinary black pigment, the kind that colors most animals, simply leaks too much. It is the difference between hiding and being spotted, between eating and being eaten. The deep-sea fish had to do far better, and they did. Reflecting under 0.5%, and in the case of omerodes as little as 0.044%, they had crossed into a class of darkness that humans only recently learned to engineer. The comparison that leapt to researchers' minds was Vantablack, a synthetic material unveiled in 2014, built from a forest of vertical carbon nanotubes that trap light and absorb well over 99.9% of it. Vantablack was hailed as a marvel of nanotechnology, a substance so dark it made three-dimensional objects look like flat holes in space. Yet, these fish achieved comparable performance with nothing but biological tissue, refined by evolution over millions of years in total darkness. That is the astonishing part. The fish are not merely painted dark, they are structured to swallow light, functioning less like a colored surface and more like a trap. To understand how, we have to go beneath the skin, into the microscopic architecture that makes their blackness possible. Slice into the skin of one of these ultra-black fish and put it under a microscope, and the secret comes into focus. The darkness is not a coating on the surface. It is built into the structure of the skin itself, and its architecture is the whole point. The key players are melanosomes, tiny cellular capsules packed with melanin, the same pigment that darkens human skin and hair. Melanin is a light absorber, but on its own, it is imperfect. Shine light on a loose scattering of melanin, and some of that light still escapes, bouncing back before the pigment can absorb it. Ordinary dark animals hit exactly this ceiling. What the deep-sea fish do differently is in the arrangement. In their skin, the melanosomes form a single, continuous, densely packed layer just beneath the surface, with almost no gaps between them. There are no clear windows for light to slip through and reflect off deeper tissue. The pigment granules are crowded together into an unbroken sheet, an uninterrupted blanket of absorber wrapping the body. This is where the physics turns beautiful. When a photon of bioluminescent light enters the skin, it does not strike a smooth mirror and bounce straight back. Instead, it hits a melanosome and is scattered sideways, deflected into the pigment layer rather than out of it. There, it encounters another melanosome and another, ricocheting laterally through the dense field of absorbing granules. With every collision, more of its energy is soaked up by the melanin. The light is not repelled at the surface. It is drawn inward and steered along a path that leads only to absorption. By the time a photon might have escaped, there is almost nothing left. This is why the skin behaves like a trap rather than a surface. Light checks in, but it does not check out. More than 99.5% of it is captured, converted to heat, and never returned to the water. The body becomes a hole in the ocean's light, a shape that gives back nothing. But absorbing light this efficiently is not just about having pigment. It depends on the precise size, shape, and spacing of those melanosomes, a geometry so exact it reads like deliberate engineering. The secret to ultra-black skin is not the pigment alone. It is the architecture. When Karen Osborne and Alexander Davis examined the melanosomes under electron microscopes, they discovered that these pigment granules were not randomly scattered. They were shaped, sized, and packed with an almost engineered precision. Each melanosome measured roughly 400 to 700 nanometers across, dimensions tuned to the wavelengths of visible light that flood the deep from bioluminescent flashes. This is no accident of biology, it is optimization. A smaller granule would let too much light slip past untouched. A larger one would leave gaps between neighbors, tiny windows through which photons could escape back into the water. Instead, the fish settled on a size that captures light most efficiently across the entire visible spectrum. The packing matters just as much. In ordinary black tissue, melanosomes sit in loose, uneven layers, leaving spaces where light can bounce cleanly outward. In ultra-black fish, they form a continuous, uninterrupted sheet directly in the outermost skin, with no reflective backing beneath them. Every photon that enters is forced to travel a gauntlet, striking granule after granule, losing energy at each collision until nothing remains to reflect. Researchers modeled these arrangements and found that the geometry itself boosted absorption dramatically. If you took the same amount of pigment and simply spread it differently, reflectance would climb. The material stays identical, but the structure transforms performance. This is why the fish outperform many manufactured coatings. Human engineers spend years designing nanostructures to trap light. These fish evolved a comparable solution using only melanin, arranged with ruthless efficiency. The lesson is profound. Blackness in the deep sea is not a matter of how much pigment an animal carries. It is a matter of how that pigment is organized in three-dimensional space. The melanosomes function like an optical maze, a labyrinth built at the scale of light waves. And here is the truly staggering part. This exact solution, this specific geometry of disappearance, did not evolve once in a single lucky lineage. It appeared again and again in fish that share almost nothing else, across the branches of an ancient family tree. When the researchers mapped their ultra-black species onto the fish tree of life, they found something that transformed a curiosity into a revelation. The 16 species were not close relatives. They belonged to at least 6 different orders, lineages that diverged tens of millions of years ago and share no recent common ancestor with this trait. The ultra-black fangtooth, the dragonfish, the anglerfish, the Pacific black dragon. Each arrived at the same solution along its own separate evolutionary path. This is convergent evolution, and it is one of the most powerful signals biology can send. When unrelated organisms independently invent the same feature, it means the environmental pressure driving that feature is enormous, almost inescapable. Wings evolve separately in birds, bats, and insects because flight offers overwhelming advantage. Eyes evolve dozens of times because detecting light is worth the cost. And ultra-black skin evolved again and again in the deep sea, because becoming invisible is, quite literally, a matter of life and death. Consider what that repetition implies. Each lineage started from ordinary dark pigmentation. Each faced the same relentless problem of bioluminescent flashes betraying its silhouette. And each, through countless generations of selection, refined its melanosomes toward the same optimal size and packing. The fangtooth and the anglerfish never compared notes. They never shared genes for this trait. They were pushed, independently, toward an identical answer by the identical logic of the abyss. The mathematics of light does not care which family a fish belongs to. A photon striking a fangtooth behaves exactly as a photon striking a dragonfish. So the physics dictated the same design, and evolution obeyed, over and over. This is why the discovery matters beyond a simple catalog of dark animals. It reveals a universal law operating in the darkness. Where light betrays, absorption wins. And the deep sea rewarded that strategy so consistently that it emerged as if summoned, across a scattered constellation of species. But invisibility is only half the story. In the abyss, the same creatures that hide from light also hunt with it, turning darkness and glow into weapons in a contest that never ends. Ultra-black skin is not a solitary invention. It is one move in a contest that has raged for millions of years, an arms race fought with light and shadow across the deep. Every advance on one side provokes a countermeasure on the other, and the ultra-black fish sit at the cutting edge of that struggle. Consider the anglerfish, one of the darkest species measured. It carries a glowing lure, a bioluminescent bulb dangling before its jaws, powered by symbiotic bacteria. That light draws curious prey close into blackness, but the same light is dangerous. If it reflected off the anglerfish's own body, it would reveal the predator waiting behind the bait. So the fish wraps itself in ultra-black skin, ensuring that its lure shines like a lonely beacon, while its body vanishes completely. The glow attracts, the darkness conceals. Together they form a perfect trap. This is the deep-sea paradox, weaponized. The dragonfish takes the strategy further, producing red bioluminescence that most other animals cannot even see. A private searchlight to spot prey without being detected. And prey, in turn, evolve their own defenses, including the ultra-black camouflage that hides them from these hunters. Predator and prey escalate together, each darkness answered by a brighter flash, each flash answered by deeper black. The result is an environment where visibility is currency and invisibility is survival. To reflect even 0.5% of light can mean detection, and detection means death. So selection drives reflectance ever lower, pushing these fish toward the absolute limit of what melanin can achieve. There is no truce in this race, no final victory. As long as animals in the deep produce light, other animals will evolve to erase themselves from it. The ultra-black fish represent the current frontier, biological light traps, refined by a competition with no referee and no end. And yet what these creatures perfected in cold darkness turns out to matter far beyond the abyss. The same problem they solved, trapping light and reflecting almost nothing, is one that human engineers have chased for decades in laboratories, telescopes, and machines of war. The problem these fish solved is the same problem that haunts human engineering. We too need surfaces that trap light and give nothing back. Inside telescopes, stray reflections scatter across sensors and drown faint signals from distant galaxies, so astronomers coat their instruments in the blackest materials they can find. In stealth technology, designers labor to build aircraft that absorb radar and evade detection. In camera systems, engineers line optical pads with dark coatings to preserve contrast. All of these are attempts to do what the fangtooth and the anglerfish already perfected. In 2014, engineers unveiled Vantablack, a coating of carbon nanotubes that absorbs more than 99.9% of light. It stunned the world. Yet the ultra-black fish reach reflectances below 0.5%, using nothing but melanin arranged with precise geometry. No exotic nanotubes required. That comparison has inspired researchers to study whether the fish's design principles, the specific size and dense packing of pigment granules, could lead to cheaper, more durable light-absorbing materials. Nature engineered in flesh what we struggle to engineer in factories. This is the deeper meaning of the discovery. The deep sea, a place we once imagined as empty and featureless, turns out to be a laboratory of extreme solutions, and evolution, its relentless engineer. Under pressure we can barely comprehend, in cold and permanent night, life converged on an answer so refined it rivals our finest technology. And it did so not once, but repeatedly, across unrelated lineages, driven by a single unyielding demand. Think about what that demand truly required. To reflect almost no light. To become a hole in the water, a shape that swallows every photon. To defeat the treachery of bioluminescence not by outrunning it or outshining it, but by refusing to answer it at all. These fish did not armor themselves. They did not grow faster or stronger. They took the most fundamental act of visibility, the reflection of light, and they abolished it. In a world where to be seen is to die, they found the ultimate defense. They engineered their own bodies into absence. To survive the deep, they erased themselves.